String girdling Earth. As most people know, Earth is round. Obviously, it's not a perfect ball. In fact, it bulges out slightly at the equator due to centrifugal force. But let's imagine Earth as a perfect ball for a thought experiment. Stretch a piece of string along the entire equator of Earth so that it loops back on itself and hugs, or girdles, the ground perfectly. Now, lift the entire string so that it's exactly 1 meter off the ground, and add extra string so that it's still a closed loop. How much extra string is needed? One's gut instinct may be to assume that it would be several kilometers at least, but this is incorrect. Let's actually work out the math. Our perfect ball Earth has a certain radius, meaning the distance from the center to any point on the surface. At the start of this scenario, the string forms a perfect circle around Earth with the same radius. If we lift the whole string up 1 meter and extend it so it still connects, the result is another perfect circle, this time with the radius being 1 meter bigger. Let's see how increasing the radius of a circle affects its circumference. We will use tau, the ratio of a circle's circumference to its radius, about 6.28, and equal to 2 times pi. A circle's circumference is tau times the radius. A circle with a radius of 1 meter has a circumference of tau meters, about 6.28 meters. For a radius of 2 meters, the circumference is 2 tau meters. A 3 meter radius yields a 3 tau meter circumference. In general, increasing the radius by 1 meter increases the circumference by tau meters. The circumference is a constant multiple of, and therefore proportional to, the radius. So, no matter the radius of Earth, lifting the string by 1 meter causes a length increase of tau meters, or about 6.28 meters. We can also prove it algebraically like this. Thus, in order to lift the whole string up 1 meter, you would need to add about 6.28 meters of string. Coin rotation paradox. Take two identical coins, A and B. Hold coin A in place and place coin B against it. Then roll coin B around coin A without any slipping for a full cycle. How many full rotations or turns do you see coin B make? This is something you can try at home. Perhaps surprisingly, coin B actually makes 2 turns during the round trip. To understand this, let's examine a simpler scenario, rolling coin B along a flat surface. For simplicity, we'll assume that each coin has a radius of 1 centimeter. For the rolling, we will track the point on the edge of coin B that starts out touching the surface, and when that point returns to touching the surface, we'll stop rolling. As coin B completes its roll, its center travels a distance equal to the coin's circumference, which is tau centimeters, about 6.28 centimeters. The total rotation of coin B is 1 turn, or tau radians, if you prefer. Now let's return to rolling coin B around coin A. Once again, we will track the point on the edge of coin B that starts out touching the surface, which is the edge of coin A here. Then, when that point returns to touching the surface, we'll stop rolling. As coin B completes a cycle, the center of coin B traces out a circle. This circle's radius is the sum of the radii of the coins, which is 2 centimeters. Accordingly, its circumference is 2 tau centimeters. In other words, coin B travels twice as far in this example as it did in the previous example, still while only rolling without slipping. Thus, coin B must have rotated twice as much, having therefore made 2 turns. Another option is to view the rotation as the combination of 2 effects. If instead of rolling, you imagine sliding coin B around coin A while keeping a constant point of contact on coin B, then coin B will rotate by 1 turn. Alternatively, if you imagine flattening out coin A and then having coin B roll across it, then coin B will rotate by 1 turn. Combining these 2 effects, 1 turn plus 1 turn is 2 turns, which is how many turns coin B made. Don't worry if you can't grasp this problem. Apparently neither could the writers of a college admissions test. On May 1st, 1982, the SAT had a multiple choice question regarding this problem, where every single option was wrong. 3 students wrote in about the error, and the tests were subsequently regraded. Staircase paradox. Given a square's side length, its diagonal length can be calculated using the Pythagorean theorem. For instance, a side length of 1 gives a diagonal length of square root of 2. about 1.414. But what if we try another way? Approximate the diagonal using a zigzagging staircase pattern, alternating between going horizontally and vertically. The total length of the horizontal portions is 1, and the total length of the vertical portions is also 1. So the total length of the staircase is 2. If we draw staircases with smaller and smaller steps, each staircase is still 2 units long. Since the sequence of staircases gets arbitrarily close to the diagonal as you go further along the sequence, we say that the diagonal is the limit of the sequence of staircases. Similarly, since each staircase length in the sequence is 2, the limit of the sequence of staircase lengths is 2. But does that mean that the length of the diagonal is 2? No, it doesn't. While it is tempting to assume that the length of the limit of the staircases is equal to the limit of the lengths of the staircases, this is actually false. The problem is the direction of travel along each curve. If you travel along the actual diagonal, then your direction of travel remains constant. However, if you travel along one of the staircase paths, then your direction of travel jumps between directly up and directly right over and over again. No matter how small the steps on the staircase, even though the staircases get closer and closer to the diagonal, the direction of travel along the staircases never gets any closer to the direction of travel along the diagonal. Well, that's the basic idea anyway. A rigorous justification requires vector calculus, which is hard to explain in a few minutes. As it turns out, finding the arc length of a curve by approximating it with little line segments connected by vertices is valid in some cases. You just have to make sure that all of the vertices lie on the curve, unlike with the staircases. Such an approximation is the idea behind our usual formal definitions of arc length. Ultimately, the staircase paradox serves as a reminder to be careful when constructing mathematical definitions. Sphere eversion. In differential topology, the standard embedding f from s squared to r cubed allows a regular homotopy of immersions ft from s squared to r cubed such that f0 equals f and f1 equals negative f. More simply, imagine a sphere made of a stretchy, bendy sheet material. This material can go through itself, but you cannot tear this material or poke holes in it, and you cannot create a crease or sharp bend in the material, or it will be destroyed. The goal is to turn the sphere inside out, known as everting the sphere. At first glance, since the material can pass through itself, this may seem easy to do by just pushing the two hemispheres through each other. However, this creates a crease around the equator, destroying the sphere. You may try some other approaches, but in fact, it turns out to be very difficult to come up with a practical method. Perhaps counterintuitively, though, the task is indeed possible. This fact was first proven by American mathematician Stephen Smale in 1957. Practical methods for everting the sphere would later be developed by several other mathematicians, such as American mathematician Arnold S. Shapiro and French mathematician Bernard Morin, the latter of whom was blind. Perhaps the most well-known method is Thurston's corrugations, named after American mathematician William Thurston. It involves dividing the sphere into guide strips, making the parts in between bulge into corrugations, pushing the caps through each other, turning each one a half turn in opposite directions, and pushing the strips through the center of the sphere. This was famously illustrated in the 1994 educational video Outside In, developed at the former Geometry Center of the University of Minnesota. Banach-Tarski Paradox. Can you split an object into parts, and then use just those parts to construct two identical copies of the original object? In the real world, no. Not to our knowledge. But in the world of math, assuming certain rules, the answer is yes. The Banach-Tarski Paradox, proven by Polish mathematician Stefan Banach and Polish-American mathematician Alfred Tarski, states that a ball can be decomposed into at least 5 parts that can then be shuffled around to form 2 balls identical to the original. Additionally, for any 2 reasonable solids, either one can be chopped up and rearranged into the other. This theorem is often illustrated with a P and the sun, and therefore called the P and the sun paradox. In order for this theorem to be true, our axioms, or pre-assumed facts, must be carefully chosen. In particular, this theorem relies on the axiom of choice. This axiom essentially states that if you have a collection of sets, where a set is basically a collection of objects, then there is a way to select one element from each set. This fact cannot be proven from the other usual axioms, so it must be assumed as its own axiom. Unfortunately, the proof of this fact is very dense, lengthy, and hard to understand intuitively. However, it essentially involves decomposing a ball into a bunch of infinite scatterings of points, which are not measurable by volume. Using simple rigid transformations then allows us to snap these pieces back together into two balls, completing the process. Paradox of enumeration. The paradox of enumeration is one of the basic problems of sets first encountered prior to the development of modern set theory. It is related to the cardinality or quantity of elements of certain infinite sets, where attempts to determine whether two sets have the same cardinality lead to a paradox. For example, consider the set of non-negative integers 0, 1, 2, 3, and so on. Does this set have the same cardinality as the set of square numbers, numbers you can get by multiplying an integer by itself? Let's call these sets A and B respectively. On one hand, you can pair each number in set A with its square in set B, which suggests that the cardinalities are the same. But on the other hand, every element contained in B is contained in A, and A contains elements that B doesn't, so B is a proper subset of A. This suggests that A has a greater cardinality than B. This issue can be resolved using a formal definition of cardinality. In set theory, two sets have the same cardinality if each element in one set can be matched in a one-to-one correspondence with an element in the other set, with no elements left over. Such a correspondence is known as a bijection between the sets. Under this definition, sets A and B have the same cardinality. This modern notion of cardinality was developed by German-Russian mathematician Georg Cantor in the 1870s as part of his work on the creation of modern set theory. The sets in this particular case are called countably infinite, as they both have the same cardinality as the set of natural numbers, and this cardinality is called Aleph null. Cardinality of the continuum. The set of real numbers, sometimes referred to as the continuum, has a greater cardinality than the set of natural numbers. This cardinality is denoted by a lowercase fractor c. In particular, consider the power set of the natural numbers, meaning the set containing all possible subsets of the natural numbers. The cardinality of this power set, 2 to the power of Aleph null, is equal to the cardinality of the continuum. However, a seemingly counterintuitive result arises when considering the cardinality of the set of all possible pairs of real numbers. This set can be visualized as the set of all possible points in the coordinate plane. In order to find the cardinality of this set, we might first try seeing if it can be put in a bijection with the set of real numbers. Given a decimal representation of a real number, the nth digit after the decimal point can be digit number n. The digit in the ones place is digit number 0, and digits to the left are numbered with descending negative numbers. Now, for a given pair of real numbers, x, y, write out the digits of each one, and then interlace these digits to create a new number, a. The nth digit in x can be the 2nth digit in a, and the mth digit in y can be the 2m plus 1th digit in a. This will always result in a valid real number a. Indeed, this process is also fully reversible and can be used backward to convert any real number, a, into a pair of real numbers, x, y. Thus, a bijection exists between the set of real numbers and the set of pairs of real numbers, so the two sets have the same cardinality. In other words, there are equally as many numbers on the number line as there are on the entire coordinate plane. This result can also be proven with cardinal arithmetic, which comes down to demonstrating that c squared equals c, that is, that the cardinality of the continuum is its own square. Since c equals 2 to the power of Aleph null, c squared equals 2 to the power of Aleph null squared equals 2 to the power of 2 Aleph null. 2 times Aleph null is just Aleph null, so 2 to the power of 2 Aleph null equals 2 to the power of Aleph null equals c. Russell's paradox. Russell's paradox was posited by English mathematician and logician Bertrand Russell in 1901, though it was actually first independently discovered by German mathematician Ernst Zermelo, who did not publish his work. The paradox is as follows. If a set contains all sets that do not contain themselves, then does that set contain itself? If the answer is no, then the set does not contain itself. But that means it has to be included in itself, which is a contradiction. But if the answer is yes, then the set does contain itself, so it shouldn't be included, which is also a contradiction. Russell's paradox presented major problems for set theory around the beginning of the 20th century. Up to that point, the common conception of a set was as a collection of objects of some sort, with absolutely no restrictions on what those objects might be. However, Russell's paradox showed that this framework led to logical paradoxes. This was problematic for mathematicians, as much of math was built upon set theory. Mathematicians at the time had to come up with consistent ground rules, or axioms, regarding what a set might be or contain. This led to the development of axiomatic set theory, as opposed to the naive set theory of the past. An axiomatization of set theory was put forward by Zermelo in 1908 in order to keep track of the assumptions made in his proof of the well-ordering theorem. In the process, this set of axioms resolved the paradoxes created by naive set theory. In the 1920s, further work was done by Abraham Fraenkel, Thoralf Skolem, and Zermelo, which yielded an axiomatic set theory known as ZFC. To this day, mathematicians generally use ZFC as the canonical axiomatic set theory. König's paradox. König's paradox was published in 1905 by Hungarian mathematician Julius König. It can be stated like this. There are a countably infinite number of finitely long sequences of words. Of those word sequences, some of them are definitions of certain real numbers. So, the number of finitely long real number definitions is also countably infinite. This means that the set of real numbers that can be finitely defined is countably infinite, forming a subset of the set of real numbers. If the real numbers are well ordered, there must be a first real number that cannot be finitely defined. But this statement counts as a finite definition of that real number, so it is self-contradictory. Though this paradox can arise in naive set theory, it is resolved if one uses the rules of axiomatic set theory. In particular, it is true that a statement about a set can be represented as a set itself, which relies on a system known as Gödel numbers. However, the language of set theory simply does not allow for the definition of true statements in arithmetic, using the tools of arithmetic itself. This is known as Tarski's undefinability theorem, proven in 1933 by Polish-American mathematician Alfred Tarski. König's paradox is related to Berry's paradox, which is another paradox related to the concept of defining numbers. It arises from the phrase, the smallest positive integer not definable in under 60 letters. This phrase would seem to define a certain positive integer itself, but that would make that number definable in under 60 letters, leading to a contradiction. Richard's paradox. Richard's paradox, created by French mathematician Jules Richard in 1905, is based on an alternate version of Cantor's diagonal argument, an argument used by Georg Cantor to show that the real numbers have a greater cardinality than the natural numbers. Similarly to König's paradox, Richard's paradox considers the set of all finite definitions of real numbers. Imagine arranging all of these definitions in increasing order of length, then ordering each definition of a certain length in alphabetical order. Based on this ordered sequence of definitions of real numbers, the corresponding real numbers can also be placed in a sequence. Using this sequence, a new real number r can be constructed. The integer part of r is 0. Then look at the first decimal place of the first real number in the real number sequence. If the digit is 1, then append the digit 2 to r, otherwise append the digit 1. Repeat this process using the nth digit of the nth real number in the sequence for the entire sequence, and you will end up with a new real number not on the list, similar to Cantor's diagonal argument. But the preceding statements make up a finite definition of a real number, meaning that real number should be on the list. So this is a contradiction. This paradox, like König's paradox, can be averted by axiomatic set theory. In order for this paradox to occur, one must be able to tell whether a given description applies to a set based on the rules of set theory itself. However, this type of self-reference isn't actually allowed in axiomatic set theory. In essence, we simply disallow ourselves from doing the thing that caused the paradox in the first place, which is required in order for set theory to be consistent. Skolem's paradox. Skolem's paradox is a veridical paradox, a true yet seemingly absurd statement regarding consistent axiomatizations of set theory. It was first discussed by Norwegian mathematician Thorolf Skolem in 1922. It states that such axiomatizations may have a countable model, yet can be used to construct a sentence stating the existence of uncountable sets. This seems counterintuitive, as a countable model must contain only countable sets. This paradox is based on two theorems. The first is Cantor's theorem, proven by Georg Cantor, which states that the power set of a set must have a strictly greater cardinality than the original set. The second theorem is the Lowenheim-Skolem theorem, stating that axioms satisfiable by an infinite structure are also satisfiable by a countable structure. Here, a structure consists of a set, along with a collection of operations and relations applying to that set. This theorem was proven by Skolem and German mathematician Leopold Lowenheim. Skolem noted that these two theorems seem to go against each other, even though this isn't actually the case. This situation can be resolved by noting that for a particular model, the term set can only ever refer to a set that already exists within that model. In order for a set to be considered countable within a given model, that model must contain a suitable bijection, with this bijection being a set itself. Skolem wrote that the notion of a countable set is considered to be relative, as a set that is countable in one model may not necessarily be countable in another. His overall writings on this subject were intended as a critique of the idea of using set theory as a foundation for mathematics, as he was surprised when mathematicians of his time began to give serious consideration to the idea. However, his attempts were unsuccessful. Today, set theory is a widely regarded basis for mathematical logic, and Skolem's paradox is primarily perceived as a simple quirk of, rather than a serious flaw with, set theory.
Hilbert's Hotel. Hilbert's Hotel is a thought experiment proposed by German mathematician David Hilbert in 1925. It involves a hotel with an infinite sequence of rooms, 1, 2, 3, and so on to infinity. This is called countable infinity, since each room can be associated with a counting number. The hotel starts out fully occupied. However, a new person shows up and wants a room. Surprisingly, you can accommodate the new guest without removing any current guests. The hotel simply moves the guest in room 1 to room 2, the one in room 2 to room 3, etc. In general, the guest in room n moves to room n plus 1. Afterward, room 1 is free for the new guest. Hilbert's Hotel can also accept a countably infinite number of new guests. The guest in room 1 moves to room 2, the one in room 2 to room 4, and in general, the guest in room n to room 2 times n. This leaves the odd-numbered rooms free for the new guests. The fact that Hilbert's Hotel can accommodate new guests despite being full is known as Hilbert's Paradox. This is an example of a veridical paradox, a statement that is true despite seeming false. Cantor's diagonal argument. Cantor's diagonal argument is a proof that the cardinality of the set of real numbers is greater than the cardinality of the set of natural numbers. The cardinality of a set can be thought of as its size. This proof was published by Georg Cantor in 1891. To prove this fact, it is sufficient to show that there are more real numbers between 0 and 1 than there are natural numbers. If this is the case, then there are definitely more real numbers than natural numbers. The proof is by contradiction. A proof by contradiction starts with an assumption and shows that the assumption leads to an impossible conclusion, thus proving that the assumption is wrong. In Cantor's diagonal argument, we begin by assuming that the set of real numbers between 0 and 1 and the set of natural numbers have the same cardinality. If so, that means each real number can be paired with a natural number 1 to 1 with no numbers left over, so let's do that and put the pairs in a list. Our list of pairs will have the natural numbers on the left and the real numbers on the right, making sure the digits of the real numbers are aligned with each other. Then, we draw a downright diagonal through the digits of the real numbers. Now let's construct a new real number. Starting at the top left of the diagonal, take the first digit of the first real number and change it to something else. For example, if it is 9, subtract 1 from it, otherwise add 1. We will put this digit in our new number. Now, go down the diagonal, repeating this process for all the real numbers in the list. So is our new number a part of the list? Well, it can't be the first number in the list since the first digits don't match. It can't be the second number either, since the second digits don't match. Our new number will always differ from any given number on the list, since there will always be at least one digit that does not match the digit on the diagonal. Thus, we have a real number that isn't part of the list, meaning we haven't achieved a one-to-one pairing, which contradicts our earlier assumption. Even if we insert this new number into the list, we can just repeat this process to generate more and more new real numbers. This implies that there are more real numbers than there are natural numbers. The idea that some infinites are bigger than others is counterintuitive, but it is a true fact. Thomson's lamp. Thomson's lamp is a hypothetical device proposed by British philosopher James F. Thomson in 1954. It is a lamp that can be switched on and off as fast as you want. Let's say that you start a timer and turn the lamp on. You wait 1 minute and then you turn the lamp off again. After another half a minute has passed, you turn the lamp back on. Each time you wait for half of the previous amount of time and then you toggle the lamp. Because the lengths of these intervals add up to 2 minutes, you will have toggled the lamp an infinite amount of times after 2 minutes have passed. A task like this with an infinite amount of actions in a finite amount of time is called a supertask. But when you are finished, will the lamp be on or off? Each time you toggled the lamp off, it was immediately followed by toggling it back on, and vice versa. Thus, it seems like the question has no logical answer, which creates a paradox. Mathematically, this is related to the behavior of a certain infinite sum. 1 minus 1 plus 1 minus 1 and on forever, and that's kind of a tongue twister. An infinite sum like this is called a series, and this particular one is called Grandi's series, named after Italian mathematician Guido Grandi. Because the result just bounces back and forth between 0 and 1 forever as you take more and more terms, the series doesn't approach a specific number or converge. So we say that it diverges or has no finite value. However, certain methods can be used to assign these series a meaningful value. For instance, you can take the averages of the results as you go along, known as Cesaro summation, which gives a value of 1/2. Thomson had heard of Grandi's series being given this value, but his thought experiment did not allow the possibility of the lamp being half on. Thus, he rejected that Grandi's series and his thought experiment had any direct relation. Gabriel's horn. Gabriel's horn is an infinitely long, horn-shaped object with a finite volume but an infinite surface area. It was first considered by Italian mathematician Evangelista Torricelli in a paper published in 1643. In order to form Gabriel's horn, take the graph of the curve y equals 1 over x in the xy plane, with the domain of x being greater than or equal to 1. Then rotate this curve in 3 dimensions around the x-axis and fill in all the points that the curve passes through, forming a surface. A 3-dimensional surface created by rotating a curve around an axis like this is known as a surface of revolution. Now imagine closing off Gabriel's horn with a cap. We can find the volume of the inside region using integration. Using slices perpendicular to the x-axis, slice the inside region into thin disks that are approximately thin cylinders. Labeling the radius of each cylinder as r, the base area of each of these cylinders is pi r squared, and the little thickness is dx, so the volume is approximately pi r squared times dx. The radius at each point is just the distance between the x-axis and the graph of the function 1 over x, so we can replace r with 1 over x. So the volume of each cylinder is approximately pi times 1 over x squared times dx. And we just have to integrate this from 1 to infinity, which gives us pi. So the volume of this region is pi. But what if we just find the area under the curve y equals 1 over x, or x from 1 to infinity? This is the same as this, which becomes this. As b grows bigger and bigger, the natural logarithm of b also grows bigger and bigger without bound, so the area under the curve is actually infinite. This is despite the fact that when we rotate this around the x-axis, the volume of the solid we get has a finite value of pi. Due to the counterintuitiveness of this fact, mathematicians at the time of its discovery perceived it as a paradox. Ross-Littlewood Paradox. The Ross-Littlewood Paradox, invented by John E. Littlewood in 1953 and further explored by Sheldon Ross in 1988, involves an infinitely large empty vase and an infinite amount of balls. A supertask is performed. At each step, 10 balls are put in the vase, and then 1 ball is taken out. Each step takes half the amount of time as the previous one to ensure that the task is completed in a finite amount of time. Now at the end, how many balls does the vase contain? The intuitive answer appears to be infinitely many. Each step seems to involve a net increase of 9 balls in the vase, so the number of balls just grows towards infinity. However, there is a sense in which the vase may be empty. Imagine that, at the start, all of the balls are numbered. At step 1, you put in balls 1 through 10 and remove ball 1. At step 2, you put in balls 11 through 20 and remove ball 2, and so on. For each step number n, the ball numbered n is removed from the vase. Eventually, ball number 1000 will be removed, then the ball number 1,000,000, and so on. Since there are no balls that don't eventually get removed, by the end, all of the balls must have come out. There is no general agreement on the solution to this paradox. Besides the previous solutions, some people think it depends on exactly which balls you take out of the vase. Others think that the problem does not give us enough information to state the answer, or that it isn't well defined. Dartboard Paradox. The Dartboard Paradox is a paradox in probability. Let's say you have a dartboard and you randomly pick some point on it. Now let's say a dart hits the dartboard at a random point. Is it possible for the dart to exactly hit the point you picked? And if so, what is the probability that this occurs? This is a mathematical scenario, so we will assume that the point is infinitely small. The answer to the first question is obviously yes. The dart can hit any point on the dartboard after all. However, since your point is only one point out of infinitely many, it seems that the probability of hitting that point is actually 0. Indeed, in a rigorous mathematical sense, this is actually the case. But you can also use the same logic for any other point on the dartboard. So the probability of the dart hitting any given point on the dartboard is 0 as well. However, this seems counterintuitive, since we said that a dart must hit the dartboard. The problem is that probability 0 does not mean impossible. In this case, what we have is known as a continuous random variable because the space of possible contact points for the dart is continuous. This is as opposed to a discrete random variable where there are only a finite number of possible outcomes, such as the roll of a dice. Continuous random variables are common in probability. For example, the normal distribution models a continuous random variable. In this case, it is often more useful to talk about the probability that a given event falls within a specific region of the possibilities. For example, you can ask about the probability that a dart will land on the dartboard's upper right quadrant. In this case, the probability is 1 in 4 or 25%. When using a continuous distribution, such as the normal distribution, the probability of an event happening in a certain region is equal to the area between the graph of the distribution and the horizontal axis within that region, which can be calculated using integration. Petersburg Paradox. The St. Petersburg Paradox is another probability-based paradox named for the city St. Petersburg, where Daniel Bernoulli studied it. Imagine a casino game beginning with a stake of $2. The stake is the amount the player will be paid at the end. The player flips a coin, and if it lands on tails, the stake doubles. Otherwise, the game ends, and the player gets the stake. We can calculate the expected value of the player's earnings. The expected value is the average value that you would predict from a random process. There is a 1/2 chance that the player lands on heads immediately, earning $2. Given the 1/2 chance of landing on tails to start with, there is then a 1/2 chance of landing on heads on the next flip and earning $4, giving an overall chance of 1/4 to earn $4. This logic continues for all remaining flips. We can calculate the expected value by multiplying each payout by its probability and adding the results together. 1/2 times 2 plus 1/4 times 4 plus 1/8 times 8 is the same as 1 plus 1 plus 1, and this is the same as infinity since it will keep going on. Now, what would be a fair cost to play this game? Hypothetically, no matter the cost, even if it was $1 billion, the casino always loses. However, according to Ian Hacking, few people would pay even $25 to play this game, which isn't a paradox. Riemann series theorem. The Riemann series theorem, named for and rigorously proved by German mathematician Bernhard Riemann, involves conditionally convergent series. A conditionally convergent series is an infinite sum that converges to a particular finite value, but would not converge if you added up the absolute values of the terms instead. In other words, a conditionally convergent series converges only under the condition that the sign of each term is taken into account, This is as opposed to an absolutely convergent series, which converges in both cases. According to the Riemann series theorem, any given conditionally convergent series can be rearranged to produce any real number. This runs counter to how finite sums work. In a finite sum, rearrangement of the terms doesn't affect the result. To prove the Riemann series theorem, consider grouping all the terms of a conditionally convergent series into two groups, a positive and negative in descending order of magnitude. Since the series is convergent, the magnitudes of the terms in each group must get arbitrarily small. However, remember that the series is only conditionally convergent. That means that each group of terms individually doesn't sum to a finite value. If the positive terms were to sum to some positive value a, and the negative terms were to sum to some negative value minus b, then the overall sum of the absolute values of the terms would be a plus b, implying that the series would be absolutely convergent, not conditionally convergent. It's also impossible that the positive terms sum to positive infinity, while the negative terms sum to a finite negative value. Otherwise, the original series would diverge towards positive infinity, not converge. This is also true the other way around. Thus, the only possibility is that the positive terms sum to positive infinity and the negative terms sum to negative infinity. Due to the fact that these are unbounded, we can combine terms to go as high or low as we want. In order to test this out, let's pick any real number x and try to get to it by adding our terms. We start at 0. If x is above us, we add the largest positive term we haven't used. If x is below us, we add the negative term of greatest magnitude that we haven't used. If we are currently at x, we can add either a positive or a negative term. We can repeat this process indefinitely, going as far up or down as we need, and gradually converging on x as our terms get smaller and smaller.
The missing square puzzle. The triangle puzzle with the missing square is one of the most well-known examples where geometric intuition fails. At first glance, the problem seems simple. Two triangular figures composed of the same four geometric pieces. These pieces can be identified as two right triangles, red and blue, of different sizes, and two irregular parallelograms, green and yellow, which are rearranged. In the first arrangement, they appear to occupy a total area without gaps, whereas in the second rearrangement, a small empty square appears. The key to the puzzle lies in the illusion that both configurations form a single right triangle. Visually, the outlines appear to match. The base, height, and hypotenuse seem to be aligned. However, upon precise analysis, it becomes clear that the hypotenuses are not straight segments, but compositions of two segments with different slopes. In the first figure, the top line has a slightly convex curvature. In the second figure, a concave curvature. This curvature, imperceptible to the naked eye, is enough to create or eliminate a small portion of area. From a mathematical point of view, this can be demonstrated by examining the slopes of the triangles that make up the figure. The red triangle has a slope of 3/8, while the blue one has a slope of 2/5. These different slopes imply that their hypotenuses are not parallel. Therefore, when placed next to each other on the supposed hypotenuse of the larger triangle, the line they form is not straight. The entire figure, then, is not a true triangle. Even when the triangles are superimposed as shown in the figure, it is evident that their hypotenuses do not match. This difference, although visually subtle, prevents the segments from aligning along a continuous straight line. They're not proportional and therefore cannot together form a true hypotenuse. The discrepancy creates an accumulated space, seemingly lost or gained, that gives rise to the illusion of the missing square. The paradox is in fact a consequence of elementary geometry being visually misinterpreted. In summary, there's no paradox or actual loss of area. There is an illusion caused by non-uniform geometry and visual trust in falsely rectilinear outlines. This puzzle highlights how perception can be deceived even with simple flat figures, and how basic concepts such as area and shape depend critically on mathematical precision rather than visual intuition. The Laves Paradox. This paradox arises from the study of tessellations. A tessellation is a pattern that completely covers a surface using repeated geometric shapes without gaps or overlaps. The most well-known tessellations are periodic. They repeat the same module regularly across the plane. Classic examples include the repetition of equilateral triangles or the hexagonal structure of a beehive or a floor design. In any case, an evident symmetry is observed. Each shape is translated, rotated, or reflected to cover the space uniformly and predictably. Traditionally, it is assumed that symmetry implies periodic repetition. That is, if a pattern has symmetry, whether by translation, rotation, or reflection, we expect it to repeat regularly in all directions. However, there are tessellations that break this rule, displaying order without periodicity, which deeply challenges classical geometric intuition. An example of this is figures such as Penrose tilings, which radically defy this visual and geometric assumption. In these configurations, there is local symmetry but no global repetition. No fragment of the pattern repeats infinitely across the plane as in a classical periodic tessellation. Despite maintaining a form of order, it creates the illusion of broken or incomplete symmetry, challenging geometric intuition. This type of tessellation, initially inspired by the studies of the German architect, civil engineer, and urban planner George Ludwig Friedrich Laves, and later more thoroughly developed by the British physicist and mathematician Sir Roger Penrose, is described mathematically using local matching rules that prevent total repetition. Additionally, it is worth noting that these structures are not fractals, as they do not repeat at different scales. By definition, non-periodic tessellations are unique patterns that are never fully replicated, balancing local order with apparent global chaos. This paradox does not represent a mathematical contradiction, but rather a visual and conceptual challenge. It forces us to distinguish between order and periodicity, between structure and repetition. This phenomenon has transformed not only geometry, but also crystallography, visual art, and the way we understand space, regularity, and apparent chaos. The Ebbinghaus Illusion. The Ebbinghaus Illusion is one of the most emblematic examples of how visual perception can distort the geometric interpretation of figures. Discovered by German psychologist Hermann Ebbinghaus in the 19th century, this illusion consists of presenting two central circles that are exactly the same size, but surrounded by other circles that vary in size. The circle surrounded by larger figures appears smaller, while the one surrounded by smaller circles appears larger, even though both are identical. This illusion illustrates a key discrepancy between subjective perception and mathematical reality. From a geometric standpoint, the size of the circles can be measured precisely: area, diameter, and circumference. Their equivalence can also be determined objectively. However, the human visual system does not process these measurements consciously. Instead, it compares spatial relationships and relative proportions within an immediate visual context. The mechanism behind the Ebbinghaus illusion is based on contextual contrast. The brain interprets the size of an object not in absolute terms, but in relation to the surrounding objects. Klein Bottle. The Klein Bottle is a fascinating mathematical object that challenges classical notions of interior and exterior. It was proposed by the German mathematician Felix Klein in 1882 as a non-orientable surface, meaning a figure that has no distinguishable inside or outside. Geometrically, it is a closed surface that cannot be represented in three-dimensional space without its surface intersecting itself. Topologically, the Klein Bottle is a compact, closed, non-orientable surface with no boundary. Unlike a sphere or a torus, it cannot be divided into two distinct sides. It is impossible to construct a true Klein Bottle in three-dimensional Euclidean space without the surface intersecting itself. The significance of the Klein Bottle goes beyond the visual. It is a key tool to topology, especially in the study of surfaces, classification of manifolds, and group theory. It represents how three-dimensional geometric intuition can fail and is one of the most iconic examples of geometry breaking conventional spatial limitations. For more on the Klein Bottle, check out our video on complex geometry shapes. The Infinite Staircase, or Penrose Stairs. The infinite staircase, known as Penrose Stairs, is an impossible geometric figure that illustrates how perception can construct realities that do not exist in physical space. It was conceived by psychiatrist and geneticist Lionel Penrose together with his son, mathematician Roger Penrose, who also developed the famous non-periodic tessellations studied earlier. It was later popularized by the lithographs of artist M.C. Escher, particularly in his work Ascending and Descending. The figure represents a staircase built in a closed loop, where each section appears to constantly ascend or descend, yet ultimately returns to the starting point. This structure defies the fundamental laws of Euclidean geometry, since if one were to ascend it indefinitely, they would end up where they began, something physically impossible in three-dimensional space. It is a clear manifestation of how perspective can deceive spatial intuition and generate an illusion of continuity. The trick lies in the use of projective geometry. Each stair segment is coherent on its own, but the combination in a closed cycle creates a visual contradiction. Mathematically, this type of figure cannot exist in three-dimensional space without distorting its components, but it can be represented in two dimensions through a precise visual construction. It is based on a carefully designed perceptual illusion optimized to maintain coherence from a perspectival viewpoint.